Once quantitative data are grouped into classes, we can visualize the distribution using several complementary plots. Histograms show how the data are distributed across intervals. Stem and leaf plots preserve individual values while offering a quick visual summary, and dot plots display each observation as a dot. Choosing the right tool depends on your sample size, measurement scale, and the story you want to tell. A histogram is a graphical display for quantitative data that shows how values are distributed across a range. Like a bar chart, it uses rectangular bars, but the interpretation is fundamentally different. Each bar in a histogram represents a class interval of numerical values, and the height of the bar shows how many observations fall within that interval, or the proportion of observations if relative frequencies are used. Because quantitative data are measured on a continuous scale, the bars in a histogram touch. This visual continuity emphasizes that values flow smoothly from one class to the next, unlike categorical bar charts where gaps indicate distinct groups. The horizontal axis is measured in the original units of the data, while the vertical axis displays either frequency, relative frequency, or density. Histograms are especially useful for revealing the shape, center, and spread of a distribution. They allow us to see whether data are symmetric or skewed, whether there are multiple peaks, and whether unusually large or small values are present. A histogram is built directly from a frequency distribution. Usually, we rely on software to construct the histogram automatically for us. However, it is beneficial to picture how one is made manually in order to understand them better. Here are the steps for constructing one. Step 1. Construct a frequency distribution using classes of equal width. Step 2. Label the horizontal axis with the class boundaries and the vertical axis with frequencies or relative frequencies. Step 3. Draw adjacent rectangles whose widths equal the class widths and whose heights equal the corresponding frequencies. The number of classes or bins strongly affects the appearance of a histogram. Too few bins oversmooth the data and hide structure. Too many bins create a jagged, noisy plot. A common guideline is to use between 5 and 15 bins, adjusting as needed to highlight meaningful patterns, rather than random variation. As with bar charts, decorative effects such as 3D bars should be avoided. They distort perception without adding information. Consider a study of the resting heart rates in beats per minute of 100 individuals undergoing physical therapy. Resting heart rate is a continuous quantitative variable, so grouping values into intervals is appropriate. The minimum heart rate is 50 and the maximum is 93, giving a range of 43. Suppose we choose 10 classes. The class width is 43 divided by 10, which is equal to 4.3, which we round up to a convenient value of 5 beats per minute. We start slightly below the minimum value at 47.5 and construct the class intervals. This frequency distribution shows how heart rates accumulate across the range. From this table, we construct the histogram by drawing adjacent bars whose heights correspond to these frequencies. Histograms transform a frequency distribution into a visual summary that highlights the shape of the data. They help us see where observations cluster, how variable the data are, and whether unusual values are present. Because many statistical methods rely on assumptions about distributional shape, histograms play a central role in both exploratory analysis and model checking. When constructing a histogram, the choice of the number of classes or bins requires care. Too few classes oversmooth the data, hiding important features such as skewness, gaps, or multiple peaks. In contrast, too many classes make the histogram appear jagged and noisy, emphasizing random variation rather than meaningful structure. A well-chosen number of classes balances detail with clarity, revealing the overall shape of the distribution without distracting from its main features. From this histogram, we cannot determine much about the structure due to the jagged shape from too many bars. Suppose the previous histogram had only 4 classes instead. Here, some of the features of the data is lost since the bars span too large of a class interval. We may want to know more on how the values are distributed in these large intervals. Fortunately, most software like JMP do a good job in finding a right balance in determining the number of classes. A stem and leaf plot is a simple display for quantitative data that preserves the original numerical values while providing a visual summary of the distribution. Each observation is split into 2 parts: a stem, consisting of the leading digits, and a leaf, consisting of the final digit. The stems are listed in increasing order in a column, and the leaves corresponding to each stem are written to the right. Because stem and leaf plots retain every data value, they allow you to see the shape, center, and spread of the distribution and recover the original data set if needed. This makes them especially useful for small to moderate sample sizes, typically fewer than about 100 observations, where displaying individual values is still manageable. Unlike histograms, which group data into intervals and sacrifice some detail, stem and leaf plots show exactly where each observation falls. At the same time, the ordered stems and leaves create a visual structure that reveals clustering gaps, skewness, and extreme values. Suppose an orthopedic clinic records the time in days for 20 patients to regain full range of motion after knee surgery. Here's a stem and leaf plot for this data. In a hand-drawn stem and leaf plot, the stems would represent the tens of days. For example, 1, 2, 3. And the leaves would represent the ones digit. Many statistical software packages split each stem into 2 rows, one for leaves 0 to 4 and another for leaves 5 to 9, to make patterns easier to see. From the plot, it is easy to see where most recovery times cluster and to identify unusually long recovery periods. Because the stems are ordered, the plot also highlights the overall shape of the distribution and any extreme values. Suppose an instructor records the quiz scores out of 100 for 80 students in an algebra course. Here, the stems represent the tens digit of the score, 5, 6, 7, 8, 9, and the leaves represent the ones digit. The stem and leaf plot shows that most scores fall in the 70s and 80s, with a few higher scores in the 90s and possibly some lower scores in the 50s. Stem and leaf plots are ideal when the data set is small enough to display individual values clearly. You want both a numerical listing and a graphical summary. Preserving the original data values is important. For larger data sets, stem and leaf plots become cluttered, and histograms or dot plots are usually more effective. However, for exploratory analysis of modest-sized samples, stem and leaf plots provide a powerful blend of detail and visualization. A dot plot is a simple graphical display for quantitative data in which each observation is represented by a dot placed above a number line. When multiple observations have the same value, the dots are stacked vertically. This stacking makes frequencies visible while still preserving the individual data points. Dot plots are especially useful for small to moderate data sets, where displaying every observation is feasible and desirable. Unlike histograms, which group values into bins, dot plots show the exact values observed. This makes it easy to identify clusters, gaps, and outliers, as well as to see the overall shape of the distribution. Because dot plots work directly with individual values, they are flexible enough to handle both discrete variables, such as counts, and continuous variables, especially when the data are rounded. They are also quick to construct and intuitive to read, making them a popular choice for exploratory analysis and classroom demonstrations. Continuing the dental theme, suppose researchers record the number of clinic visits per patient during a year for 25 orthodontic patients. The variable of interest, the number of visits, is a discrete quantitative variable. The dot plot shows that most patients had between 1 and 3 visits, while a few had no visits or as many as 13 visits. Because each dot represents a patient, the plot makes it easy to see both the concentration of values and the less common outcomes. Dot plots are an excellent choice when the data set is small enough to display individual observations clearly. Exact values matter. You want to quickly identify clusters, gaps, and outliers. As data sets grow larger, dot plots can become cluttered and difficult to read. In those cases, histograms provide a more effective summary. For small to moderate data sets, however, dot plots strike a valuable balance between numerical precision and visual insight. To recap, histograms reveal the overall shape of a distribution and are most useful for moderate to large samples. They sacrifice individual data values to provide a smooth picture of the distribution. Stem and leaf plots preserve actual data values and work well for small to moderate samples. They quickly show the shape and allow you to recover the raw data. Dot plots also preserve individual values and are easy to interpret for small data sets. They can handle discrete counts and continuous measurements.